Hello, it's David at DSES UK, and oh my, that last video was something of a rant all round, so it's back to some good old-fashioned eggs and bacon, tedium-free electrical nonsense. And speaking of nonsense, someone left an incorrect comment on that prior presentation, a myth I shall today dispel, seeing as it's not the first time I've heard it. The erroneous assertion came about when I said I'd installed residual current protection on a lighting circuit that lacked a protective conductor in a domestic dwelling, only to be told it was pointless as a residual current device cannot operate if a protective conductor is absent. Which would be true if we were in an electrical environment that was wholly earth-free, which, even if it were the unlikely case in my commenter's house, certainly isn't in most abodes, such as, for example, your mum's, who's opened up her front entrance to me enthusiastically and quite frequently. But perhaps we need to start with some basic physics. Your house is fed from a local transformer. On the primary side of that transformer is the high voltage supply from the grid via a power station with all pylons and shit. But anyway, we're not interested in the primary side at all, as it's the secondary side of the local neighbourhood transformer, which is the final part of the transmission chain that does the job of stepping down the high voltage from the grid to the low voltage we want delivered to our homes. That is 216 to 253 volts here at the UK at the time of recording, although there are steps afoot to change that for better alignment with Europe. However, let's dispel such pillow talk for now, as it doesn't get anybody's cock hard or give your mum a wide on. Nonetheless, that local transformer is pissing out 3 phases, which get split and delivered to nearby buildings, usually single phase domestically, but a larger property may have 2 or all 3 phases. To keep things simple, I'll redraw this artistic asshole to concentrate on just one phase going to one property, that phase being a nominal 230 volt with respect to Earth. And by Earth I do mean the physical ball of shit-smelling dirt we're all squatting on and ruining as it hurtles around the sun. And no, it's not flat, this is a channel for drunkards, not fucktards. Hit the thumbs down and click off now if you fall into the latter category. Back onto topic, and coming off that secondary transformer coil is a line wire at 230 volts and a neutral wire at 0 volts. That neutral is referenced to physical earth, and with those neutrals probably in multiple places, hence the term protective multiple earthing, or PME. When it gets to the service head in most modern UK homes, the neutral and the protective conductor are split into 2 distinct wires that each serve a different purpose by essentially doing the same thing, that thing being to carry current back to the transformer. Well, okay, I'm simplifying current flow as being in one direction, but this is AC, not DC. It just makes it easier for all the damn slides I have to draw for this one. If we just stop at the service head here, then we find fuck all is happening. Sure, a voltmeter between line and neutral will show a potential difference of 230 volts, as will a reading between line and earth, but no current will be flowing as there is presently no load. So okay, smart guy, let's go stick on a load, something located between line and neutral after the head, in this case a toaster, via an RCD and breaker that would be located in the consumer unit. What we have here now, aside from a graphical headfuck, is a closed loop system, most easily pictured as current flowing from the transformer down the line wire to the load, which happens to do something jolly useful with it in a controlled way by taking only as much current as it needs thanks to its resistance, or impedance if you want to be a dick about it, because there may be capacitive or reactive elements to said load. And look, in this case it's just a fucking toaster, so it's resistive. Let's not overthink the thing. I'm already simplifying it enough. So load current then leaves the load by pissing down the neutral wire through the head and back to the transformer. Physics 101 says, aside from the earth not being flat, that current always has to flow in a loop from source through load and back again. If you break that loop at any point, like here where the breaker is clocked off, then the current stops flowing and your bagels, muffins or hot cross buns don't get toasted, although personally speaking a non-toasted hot cross bun isn't a bad thing. While the blue neutral conductor is used to carry the load current, the green-yellow protective conductor is present for any fault current, of which there should be none if nothing's cocked up by some prick wearing a NAPIT or NICEIC logo. Our protective conductor runs from the intake position via the CU and socket outlets to a touch-accessible metal part of your mum's toaster, where if we turn it off, I can introduce my cock up your mum's brown hole. No wait, I'm getting confused. I mean, the cock up is the brown line wire popping out of its terminal hole inside your mum's toaster. Yes, that's it. And coming into contact with the metal casing. When the breaker is flicked back on, this fault shorts out before the resistive heating element, which itself would usually control and limit how much current can flow. So we now have a situation where there is no resistance aside from a tiny amount in the wires themselves, and our current therefore becomes large and uncontrolled, albeit still flowing in a loop as before, except this time it's through the earth fault loop path and not the usual neutral path. Although the RCD here will probably react quicker, this is where our fuse or breaker is designed to speedily step in, and hopefully before the wiring gets as hot as your mum when I'm dropping my tough-built trouser belt around my honeydee waltz in front of her. In many countries, the circuit protective conductor is the same size as the line conductor. However, here in Middle Earth, which is still round and not flat, we get to save on copper and cable sizing by using a reduced radius of CPC in our building wiring. The assumption being if the circuit is installed and correctly protected, then the protective device will operate in a timely fashion. And although it would exceed what the smaller cross-sectional area of our protective conductor can withstand, the duration ought to be short enough so that damage won't occur. Proof, if it were needed, that size isn't important and it's all about the action. As verified by your mum, whose tongue is lolling out and drooling whenever she lays her eyes upon my massive throbbing purple-ended cock. The fault current in this example flows down the protective conductor through the service head and back to the supply transformer because that path has a low electrical impedance it's happy to whip down like your mum whips down me. But let's say your mum's toaster's metal casing doesn't go live immediately because the fault is after the heating element and therefore doesn't manifest itself until she plops her tea cake into the fucking thing and while she is still in touch contact with the metal casing. Can we have that graphically? Oh yeah, right, you wish your mum looked like that. I wish your mum looked like that. What the fuck is this, her letsgodogging.com profile picture? It somehow doesn't hold up to reality, methinks. Nonetheless, her bread product has been duly inserted and she's still in contact with what is now live metalwork as she, rather expertly, yanks off the plunger. Here, the protective conductors once again provide a low impedance path of the transformer, so fault current, wanting to take the easiest route of return to the point that's referenced to Earth itself, happily traverses through the wiring rather than via the more awkward route that happens to be through your mum's womanly curves, along with the physical ground she's standing upon. That is why we have protective conductors and earthing as our primary means of shock protection. It provides a better path for fault current than anybody's body does. If I put a continuity tester across my thumb here, even though this instrument can read up to 2000 ohms, it's still off scale high because my skin is a pretty crappy conductor when it comes to the small potential being applied. It might be different in a damper environment, if I had an open cut or wound, if I were sweating out the salts like I've just smashed in the back doors of your mum. But here today in the dry and fully clothed confines of the cave, not so much. If I were to increase the force or potential by switching to the 250 volt insulation resistance function, however... Oh, you fucker. Well, I can feel that all right. And that's because absolutely everything has resistance to the flow of current. It's just a question of how easily that resistance breaks down. Copper, gold, aluminium, steel, brass, they naturally have low resistances and are examples of good conductors. Materials with high electrical resistance are, of course, insulators and include glass, plastic, ceramics, rubber and wood, and not the kind of wood I get over your mum. No conductor is perfect, however. They all have resistance to differing degrees, and no insulator is perfect either. Any material will break down if a high enough potential is applied to them. You can get glass to conduct if your electromotive force, EMF, matches your mum's lust to break down even the most determined tradesman's resistance. And let me tell you, she does like it up the tradesman. Let's use the air in the cave here as an example of insulation breakdown. It's a dry 24-ish Celsius, and this Chauvel Anu 6513 instrument, if I hold down this button, will put out 1000 volts DC. Now, that's enough potential difference, enough EMF to overcome the resistance of the air between the end of the probes. You're basically not going to be able to see this very well. But that will arc across a tiny air gap. I have to touch the probes to kick it off, and if I just widen it just by a fraction of a millimetre, it will overcome the insulation resistance of the air between the two probes and arc across visibly. There we go, that sustained it. I don't know if you saw that. So let's ramp shit up to 10,000 volts. Oh, I'm trying not to shit myself here, but you can hear the thing angrily fizzing away. We've got a transformer here at 10 kilovolts, and 2 legs connected to the output of this transformer. And if I start closing those legs, we should get some fireworks, which is opposite to how things work with your mum. And that's because a wide gap, there's too much insulation resistance to the air in between these probes for the potential to overcome the EMF, to overcome the insulation resistance of the air. But once we start closing that gap to about 20 millimeters or so, well, we get a sustained arc, and then I can start pulling it open to a point where, again, the gap's too big, the insulation resistance is too high, and it collapses. In theory, I should be able to touch the copper end of just one leg of this HV transformer and not get a shock. I'm now at a potential of 10,000 volts, yet even if I touch this earth bar with my other hand, there's no current across my beer gut, and that's because of the law of physics which says current must flow in a circuit. Here, my 10 kilovolt transformer, again incorrectly shown as the diagram should indicate many more windings on the secondary side. Nonetheless, that secondary coil is not referenced to earth, so the current has no business trying to get to ground. Oh sure, the primary side is referenced to earth back at my supply, but the high voltage output on the secondary side has no direct electrical connection to the primary side, as the transformer's magnetic field isolates the output from that earth reference. Effectively, although I'm now fizzing at a 10 kilovolt potential, nothing's going to happen here unless I'm stupid enough to simultaneously grab the business end of the opposing transformer leg, as that would complete the current loop with enough potential here to cross my manly figure. Your mum isn't going to get a shock from her battery appliances because however wet she is, her skin has a high enough insulation resistance to block any significant current flow from the extra low voltage of such gadgets and gizmos. The 230 volts AC being delivered at 60 to 100 amps to her home though, well, that's another story. If your mum fondles her toaster, not a euphemism, and the metalwork is live without that low impedance earth path for the volt current to flow down, then maybe she'll be okay for now if standing on a carpeted or wooden floor. If it's concrete, damp and or in contact with physical earth or earth surfaces, and she's not wearing those high heels I happen to like, then your mum's chance of getting away without shock decreases, because AC current can cross a capacitive path, if not a direct resistive one, to get to that physical ball of mud we're all stranded on. Despite being sweaty, because I've just had her, your mum's body resistance will be relatively high, and the fault current therefore relatively low, but it only takes about 50 milliamps to stop her heart, and the voltage being applied is enough to increasingly break down her body's insulation resistance, allowing a current at or above that magnitude to flow. Although your mum does like a buzzing appliance, that doesn't apply to her live and humming toaster, because even if she is insulated from physical ground, should she happen to touch up the toaster at the same time as something else, say the washing machine, which here is connected to a working outlet correctly connected to the building's earth, then the fault current will have no qualms zapping through her to get to that lovely grounded metalwork. If we go back to our earlier fault where the protective conductor was present on a direct line to earth short, then the fault current flowing to earth as before will cause a protective device to trip. The RCD is most likely with this fault, and within 0.3 seconds when a leakage current below 0.03 amps is detected. But should that device fail, or if there is no RCD, then the breaker will supposedly operate within 0.4 seconds in this scenario, assuming a fault current somewhere around 48 to 80 amps. These are electromechanical devices, and you have to hope they're in order. Hopefully your mum gets nothing more than a tingle, which I know she happens to like, although she's pissed off because she fancied a post-coital slice of toasted fruit loaf and instead the bloody power's gone off. Thankfully a decent electrician is in her bedroom ready to pull his trousers back on in one of those rare scenes from 70s porn films where the bored housewife does actually want the tradesman to turn up and fix the fault. Perhaps that fault isn't a clean line to earth short, however, and maybe it has some resistance, let's say a nice round 1000 ohms between line and earthed metalwork before the heating element. If we bring logic into it, again I'm sorry flat earthers, in the form of Ohm's law, we see that 230 volts across 1000 ohms means we'll be getting a fault current of nearly 1/4 of an amp down the protective conductor. This time the overcurrent breaker will do nothing. It's rated to carry 16 amps and less than 1/4 of 1 ampere is flowing. The breaker doesn't care that it's fault current, that the toaster isn't even switched on, or that the return path for that current within the building is via the protective conductor and not the neutral conductor. It'll allow that current to flow and the toaster's metal casing to remain live all day long, while sitting there with its thumb up its arse. Something I know your mum happens to like. Now, if your mum touches that metalwork in the pursuit of cooking a crumpet, and I know she likes to gobble one off, we're relying on the fault current taking the easier path to earth, which is via our 1000 ohm fault and protective conductor path. While in touch contact, her body, footwear and the floor she's standing on provides a comparatively poor alternative route to earth. Nonetheless, she is now a potential parallel path that some amount of fault current can take. How much current depends on numerous factors, but she herself has a human body full of wet bits, especially when I'm around, and an internal resistance of only about 300 ohm going by the probing I've performed, her skin being the principal barrier against shock with a resistance of 1000 to 10,000 ohms according to the Google. And remember, with our 1000 ohm fault already inside the toaster, the potential current is up to 5 times more than it takes to stop the human heart before we begin fucking around. So we don't need much of it spaffing across your mum's tits to finish the night off. Which rather reminds me of a visit I paid to her a week last Thursday. Thankfully, of course, for additional protection, we have our 30 milliamp RCD, which works by monitoring the current passing through line and returning back through neutral. An imbalance of just 16 to 30 milliamps caused by current leaking out of circuit, whether that's going down a protective conductor or going down on your mum, results in the RCD clicking off and cutting the power. And this is where the confusion from my commenter comes in. He assumes it's the current flowing down the protective conductor which has tripped the RCD. So he asks, what is the point of installing an RCD if there is no protective conductor? Okay, so let's reset with the RCD back on, your mum slipping out of that last little black number, and no protective conductor at all. Fucking madman, I know. Well, straight away our fault current is gone. The RCD isn't tripping because there's no current flowing now that we've removed the return path. Sure, the line wire is buzzing at 230 volts, as is that toaster's casing through the 1000 ohm fault still sitting between live wiring and the metalwork. Yet it's giving no outward appearance of anything even being a hazard until your mum once again pops along wanting to warm up her focaccia. Focaccia? I'll fucking focaccia. However, so long as your mum is isolated from physical earth, she won't be quivering in her usual raunchy, gasping way, as there's perhaps still no current flowing. Although if she's standing on a damp concrete floor without her fuck me boots, or if she's touching the nearby washing machine, which is perhaps still earth through a copper water pipe, oh well, sure, it's a shit path to earth, what with the 1000 ohm fault resistance combined with the resistance of her body, but nonetheless it bites, and as it bites it breaks down the insulation of her skin, which results in more current being able to flow in a vicious cycle until she ends up hopelessly dried out. Like your nan.
Young man.
Thankfully, if an operable RCD is present, then it might not come to the usual sticky end, because before the touch voltage can climb to 50 volts and before the fault current can breach 30 milliamps, the RCD clocks off the power and saves your mum's sweet ass for the electrician to visit another day, and all in mere milliseconds. You can't rely solely on an RCD for shock protection. Regulation 415.1.2 states such, and that's because an electromechanical device could physically fail. This is why Class 1 equipment like a toaster must be on a circuit that has a protective conductor connected back to a functional main earthing terminal. My commenter also said good luck getting the RCD to trip with no protective conductor, but luck doesn't come into it, my friend, because I can demonstrate it here with the aids of my intimate inflatable friend. This fluke socket tester shows 2 green lights, which indicates correct polarity and earthing, and my MFT here is showing the expected voltage both between line and earth and line and neutral. So, okay, let's rip out the whole earthing system to this entire apparatus from the head down here by pulling out the main earthing conductor entirely. None of this is now earth. We have 1 green light, which indicates no earth, and on our tester here we have no voltage between line and earth anymore, just showing a voltage between line and neutral. Pop quiz, hot shots. Seeing as there's no earthing to this entire board, and according to my commentard, no point in even having an RCD present here without it, would you expect this RCD to trip off and protect me if I touch any of the live parts of circuits downstream from it? Fuck off if you think I'm going to do that. My expectation would be that I would get a jolly uncomfortable zap and soil my trousers again at worst, but hopefully that's all, because this RCD protection is indeed still as spicy as your mum after half a bottle of fizz and a win at the bingo. Nonetheless, I'm not prepared to put my life on the line for a probably by now hopelessly demonetised YouTube video that nobody is still watching, but my erstwhile inflatable colleague here doesn't mind being directly connected to live parts albeit with a few modifications to make him a little more human. These resistors represent his body resistance at a total of 8,100 ohm, because, spoiler alert, despite appearances, he's not a real boy. Sorry ladies and gays. So we have to simulate what he represents electrically. So here's the setup. We have a live path through the RCD and MCB and touching the appliance metalwork like I touch up your mum, but we've no main earthing or circuit protective conductor in play. Our resistive representation of our plastic pal's body works out at the upper end of the 1000 to 10,000 ohm range generally given for external body resistance, and the maths says they should allow up to 28 milliamps at 6.5 watts. This is a 30 milliamp RCD and it should react in time, as ramp testing it shows it popping at 26.4 milliamps. To simulate simultaneous touch contact between this live metalwork and either another earth surface or appliance, or even the physical ground he's standing on, I have a section of aluminium foil that is itself grounded. But again, there is no earth at all on the supply circuit or the consumer unit containing the RCD. Maths and physics says that this RCD is going to do its job. Okay. Well, at the moment there's no power at all to the rig. I've got it switched off at the breaker at the other end of the cave while I prat about. So what we have here is a wire coming off this 32 amp breaker downstream of the RCD. It goes to the metalwork of our toaster. From the metalwork of our toaster through our resistive representation of our chap here, and then off to the aluminium foil that is earth that he is standing upon. So although there's no CPC or even protective conductor at all at this board, it's still hanging out down here. When I go and turn power on over there, my expectation is that this RCD will trip. So you'll keep your beady little eyes upon this device here while I go and turn this on like I turn on your mum. 3, 2, 1. See that? Popped straight off. Little action replay for you. There we go. The RCD reacted to my clicking the breaker almost as quick as your mum answers the door topless when I push her doorbell. And if we trace the current path, it's from the transformer through the head, RCD and breaker, through the socket and to the toaster's casing. From here it's not got a clean and easy path back to the transformer, but with our lad touching that live metalwork, there's enough electromotive force to break down the 8,100 ohms of his body, and as he is grounded through simultaneous contact either with other earth surfaces or with the earth itself, well, he becomes the route current can take to get back to source. And what do you know, that current imbalances the RCD because it's above the trip threshold, it's flowing down line and there's no current coming back down the neutral path, therefore it trips and power is removed. So yes, RCD operation doesn't rely on a circuit or even a whole installation having a working earth unless you're in an installation that is itself wholly isolated from earth, as detailed in Regulation 418, which doesn't apply to dwellings. Another thing I saw was someone questioning the wisdom of IR testing the live conductors of a circuit with no CPC, but again, lack of a CPC does not mean there cannot be an earth fault. Wiring or accessories might be compromised and in direct contact with earth surfaces such as copper pipes, or indirect contact thanks to something like moisture getting between live parts and grounded metalwork. So yes, it's important to check for such with requisite inspection and testing, and one would accomplish that at its most basic level on a non-earth circuit exactly by testing live parts with respect to the main earthing terminal and looking for a result in the millions of ohms range. Seeing as we've been speaking of transformers and protection against shock, we should perhaps talk about your mum's shaven haven. No, I beg your pardon, I mean her shaver socket, which you'll find in many a British bathroom as the only plug and socket arrangement permitted by BS 7671, standard outlets being a no-no within 2.5 metres of a bath or shower basin. Thank you, Regulation 701.512.3. And that's something I used to ascribe to nanny state protection. After all, people ought to be able to think for themselves and take their own risks. But seeing as our species seems to be fast evolving in terms of intelligence, saving morons from themselves might be seen as some kind of duty of care. Although personally, I don't give a fig if a flat earther or two wants to perch a toaster precariously onto the side of their bath so they can brown their bagels while doing something inappropriate with a bottle of matey. Rather sneakily, when I last remodelled my own bathroom, I did install a standard socket outlet and well within 2.5 metres, BS 7671 be damned, because I want to run a dehumidifier in here and I accept the risk of it being present, although my outlet has inbuilt RCD protection at 10 milliamps on an earthed supply circuit, itself protected at 30 milliamps for some extra belt and braces. But I digress, and going back to the humble shaver socket, this works just like my 10 kilovolt trouser stainer we saw unfortunately in action earlier, except that it has 2 taps off the secondary coil to provide both 115 and 230 volt outputs. These are considered safe for bathrooms because it's an isolating transformer. That doesn't mean you are isolated from the spicy voltages, rather that the output is isolated from earth. Therefore, even if your mum steps out of the shower, wet, naked and steaming, and she happens to touch any one of the outputs on its own, she won't get zapped because the current path wants to get to the 0 volt of its own little local transformer and not through anybody's bodily resistance to earth to return to the neighbourhood tranny. I have a shaver socket right here in the cave that's been modified with 4mm banana plugs to allow easy access to a voltmeter. So let's put one on the 115 volt terminal here. We're getting 129-ish volts. And let's see if we get something as saucy as your mum on the 230 volt terminal. 253. It's probably slightly higher here because it's presently under no load. So we know we have output voltages here, yet if I grip the metal shaft of a non-insulated tool, like your mum grips the shaft of my tool, etc, etc, I can push this into any one of these holes while holding the metalwork and not get zapped. I can even be in simultaneous touch contact with my reconnected earth bar here. And again, there's no current across me because the voltage we see here is only referenced back to the transformer that's inside here and not to earth. It only wants to get from the red terminal to the black terminal. Doesn't give a fuck about this. So okay, if that works and makes things safe without having to worry about protective conductors at all, why don't we have these transformers in all our socket outlets? Well, for a start, it would make such accessories about as bulky as your mum and nowhere near as cheap. If I open up an old shaver socket here, we can see the transformer is quite the lump. How this example works electrically is the line terminal goes into the primary coil, and on the output of that coil is a thermal fuse which connects to a springy metal bar. This example is mechanically broken, but when working, if one were to insert a suitable plug into either the 115 or 230 volt outlet on the faceplate, it would push this bar onto a contact connected back to the neutral terminal, thus completing the primary side circuit. One limitation here is the rating, this transformer being just 20 volt amps rather than a number in watts, because a transformer is a reactive rather than a resistive load, so we can't just multiply current by voltage because they're out of phase with respect to one another. I don't want to get into this too much here as I did the whole AC thing on another boring video, but 20 volt amps divided by 230 volts gives us only about 860 milliamps to play with, which would be fine for driving small loads, but let's look at what happens with something that has a larger demand. Before this thing gets buggered, like your mum, let's check the resistance of the windings. The primary is 138 ohms, so the 230 volt secondary should be about the same, as it would be wound 1 to 1. Okay, a little higher, 159 ohms. The 115 volt output should have half the winding, so about half the resistance. We're getting around the 55 ohm mark. I fucked off the thermal fuse from spoiling any party, so we're in it until we fry it. We are energised, and the tran is somewhere near room temperature at around 26 degrees. I've got the 230 volt output wired to a standard BS1363 socket outlet. No circuit protective conductor, of course, as none is needed, because even though the fan heater I've plugged in is a class 1 appliance, the supply is no longer referenced to earth. We're reading a handful of milliamps buzzing through the primary winding while idle, and if I switch on the fan motor, we seem to have no problem delivering the requisite power with this fan happily blowing like your mum. Switching to the 1 kilowatt heater setting, however, and we bomb out at half an amp instead of the 4-ish amps this appliance requires. Needless to say, our heater can't do much with that. In fact, the only thing that is getting hot in front of me, besides your mum, is the bloody transformer itself. Switching to the 2 kilowatt setting doesn't help, although it doesn't change anything other than the tranny temperature. That's because the current is being limited by the transformer's reactance. A magnetic field is created and destroyed across the primary coil with each cycle of the incoming AC waveform, and every time the magnetic field collapses, it creates a back EMF which pushes against the current from the supply. This is exactly how a magnetic ballast in an older fluorescent lamp limits the current, as I've waffled on about before. This reactance, along with the resistance of the wire in the coil, makes it increasingly harder for current to flow, and you can even see it decreasing slightly on the display here as the temperature rises. This fight against current creates heat, which creates more resistance, which creates more heat, and so we have a thermal runaway happening, and that will either result in a hotspot at some existing defect in the winding causing a break and it going open circuit, or the winding insulation will burn off somewhere and cause a short, which will blast off with some fireworks. Fire extinguisher on standby, let's see what we get. After a few minutes the current suddenly plummets. We reach a high of 129 degrees and, like when I get too drunk to do your mum, there are no fireworks here, just disappointment, mixed with a fishy smell in the air. After cooling, sure enough, the primary coil is now open circuit. Our 138 ohms of goodness is gone, so shaver sockets, fine in bathrooms for very limited loads, no good elsewhere around the home outside of perhaps powering small items. A quick post-mortem shows the core is made up of many individual metal leaves rather than a solid block, which I think is to do with reducing eddy currents, and it's quite amazing that the wire inside is thinner than one of your mum's pubes and is wrapped around this core thousands of times. And remember, despite appearances, this is an insulated conductor, as I can demonstrate. Even if I stick an ohmmeter onto this whole block of the stuff, we get no continuity thanks to the insulated coating around each strand. If I switch to insulation resistance at 250 volts, there's still no reading. Switching to 500 volts and we're still off scale high. Fuck it, let's go 1000 volts. Oh, that made me jump. 1000 volts was enough to overcome the air gap between some of the cut ends, giving us a bit of snap, crackle and pop. This was a very long video to answer one very quick question really, which is it worth having RCD protection on a circuit that has no protected conductor? And the answer is yes. Because as we've demonstrated, even with no CPC, even with no dedicated protective path for fault current to flow down, you become the path for fault current to flow down if you happen to touch something that's live. So it's better to have that device up front to save you if push comes to shove. Can't believe it took so long to say that. Let's get on to the coffee shouts.
My hangover can be my USP today. Let's hold on to do this. Just wait. Oh God. Oh shit. Right. I'm alive.
Are you sure?
Yeah.
You don't look it. Somebody's got a dreadful hangover. And for once it's not me. I've only had one, well, I say one alcoholic drink in the past week.
It's pretty much
I did have a couple of swigs of your brandy yesterday, but somebody else polished off the whole bottle and has been very ill today.
But
I have to talk very quietly.
No, please don't. I came to work.
You did,
Are
yes,
you impressed?
Yes. And we've done a job already today, haven't we? We're about to go off and do another one.
You fattened the hamsters, do you remember?
I thought they were guinea pigs.
I thought they were, that's right.
You can't keep small rodents anywhere.
I was thinking
not safe.
I was thinking of Nigel's bum or something. Wasn't there a hamster joke in there?
So was I, curiously enough. Let's get on with some facts. This has been a dreadfully long video, and I'm sorry about all the your mum jokes. They fell flat on their face, but...
You've been doing Jamie's mum again?
Well, somebody's got to. I stepped up to the plate. So let's start with our we've got a few coffee shouts. The last video was fairly popular as far as moaning goes. Nice to do something electrical on this one. Actual electrical content, as Jamie
Oh, I know which one the last one was.
Well, would you like to read out? Well, give us a name if you would.
I'll give you a
got
name.
A screen in front of her there.
Right. There's a hall. Stevie C. And the place to be.
Stevie C and the place to be. Yes, thank you, Stevie C, our man in Scotland there. He keeps threatening to come down and have a pint. So we met him at Alex last year in person for the first time. Be nice to see you again, Stevie.
Tesco can go and have a pint with them. They're in Scotland too.
They are, yes. I'm not sure that Scotland is
big
particularly
enough.
small.
Big enough.
But well, maybe you know each other. I don't know. Well, there you go. Another whore.
Andy W.
Andy W, who says that he's looking forward to more of your adventures. He says, well,
yours.
Well,
do you have
adventures?
Our
adventures. This, such as it is as adventurous as we get.
That's not. Sorry, I was thinking hamsters again.
Heck on
can't help it. Right, moving swiftly on. A virgin, Chris A.
Chris A. Yeah, Chris A. I've had a Chris B before and a Chris with no A or B. So this is a new one. Virgin, Chris A. Welcome to the world of dreadfulness, Chris A.
And thank you. After Chris A.
Another
who is?
Keith Whitehead.
Oh, sorry.
Yeah.
Keep up with the back. Keith Whitehead.
Well done. You got there in the end. No, thank you, Keith. Nice to hear from you again. We have
another virgin.
Another virgin.
Ben Poulter.
Ben Poulter from Toolbox Talk for Electricians. Go check out his channel if you're not familiar. Nice to hear from you, Ben. And we've had a few times at the various shows, and he's the first to leave a video message. I didn't even know you could do that. Buy me a coffee. So
really,
well done for being both a virgin and for being the first to leave a video message.
Try out new exciting things.
Car in front of us here, and I think he's about to hit somebody else. So that's very exciting. I might have to turn the camera around if he does that. He's certainly taken an age to part.
It's because he's old.
Right. Okay. And we have one more virgin on the Buy Me a Coffee.
Robert Smith.
Robert Smith. Wasn't he a singer, or am I thinking of somebody else? Who's the singer of The Cure? Is that Robert Smith? Maybe it's the Robert Smith, if indeed there is the Robert Smith. Certainly a Robert Smith. But I'm wittering on now. Let's move on to Superwanks.
So there's a David Patterson. Patterson, so I can't read.
Yes,
I can't read. It's too far away.
Thank you, David Patterson. I think David's contributed via Buy Me a Coffee before, but this time he's gone through the YouTube to make his contribution. Thank you, David. It shall be unwisely spent, not on brandy, at least not today. And a virgin.
A virgin, and I can't do
number. See if you can read that. 3RCANX. Oh, rolls off the tongue, doesn't it?
An anonymous virgin.
Well, nice to have you here, 3RCANX. It sounds like a robot.
Maybe
3RCANX.
Don't start.
See, I can do robot and I can do James Bond. They're my two impressions.
But you're allowed to do that. It's making me nauseous. No. It makes me nauseous.
Is a whore.
It makes me nauseous, please.
EF7480 also sounds like a robot, most money penny.
Do you know that you really shit at doing that accent? It just doesn't sound like James Bond at all.
It's the only one I got. You can't put it down. But thank you, EF7480. You know what? You keep confusing me because you keep changing your username, EF7480. I know who you are. You keep on moving things around. It's been EF780 and.
Are you serious?
Yeah. Well, assuming it's the same contributor. It's cocking up my spreadsheet.
And we'll have another virgin.
You're not going to be able to say this one, are you?
Rossi Earl.
Oh, I say. Rossi Earl, yeah.
It is.
Well done. Okay.
Huh?
Yeah.
And?
Sharp.
Another super wank is the anonymous Mark Eastwood.
Very good. Anonymous Mark is once again being far too generous, contributing to the INAEC hosting costs. And for those who are in the INAEC or proudly using its protest logo over the likes of NAPIT and NIC, do send me pictures via the admin@inaec.org email address. Do send through some photographs or some pictures of it. Or send me.
Or would you like a sticker? Or
well, I haven't got it. Either send through how you're using the image or where I can find.
I thought you said someone downloaded one. Oh, I'm just talking shit.
I'm trying to get into bed with a printer who can do stickers on demand.
That's what you said. Yeah. Sorry.
But despite inquiries thus made thus far, I haven't got anywhere. But if you are using it, then do some examples of how it's being used. I might put together a rogues gallery of us rogues who are booking the system. Booking the fucking system. Quickly onto monthly periods, because I'm aware this is taking far too long and we both need a wee.
And their car's threatening to crash into us.
Yeah, I know, this is a terrible car.
The old people parking. Mr. Humbug, thank you again.
Mr. Humbug, always.
I've got my mug.
Oh yes, here's a picture of Linda's mug overlaid on the screen right now. She actually bought a mug with Humbug on it, but sadly it doesn't have Mr. But she was thinking of you when she bought the mug.
I'm going to put Mr. on with my label maker.
Or Tipex. Just throwing it out there.
I don't do messy things. Tesco Junkies.
Tesco Junkie, do go look up Stevie C and the Place to Be, because you're all in Scotland, you know, and how far away can you be?
Look, it's a purple car. Yeah, it's lovely.
Oh, that's very curious. It's a shame it's not on camera. Jay Sargent.
Jay Sargent.
Jumping in there.
Thank you, Jay Sargent.
Good old Jay Sargent.
And Sir Jim Hook. How do you do it? You salute, don't
salute,
you?
Sir Jim Hook.
Sorry. Down under.
Down under, yes.
I wonder if he knows my sister.
Well, again, Australia, how big can it be? If your sister's down there and Sir Jim's down there, then, you know, maybe they've bumped heads.
Absolutely. Jonathan Blankley.
Jonathan Blankley, yes. Boy, I'm forgetting the name right. It's more than Dan was able to do on the last video. But always bringing up the rear is our Jonathan Blankley. And we have just one quick special mention to Mark for having a chinwag with me at CEF recently. I hope your NIC assessment went well, Mark. Probably better than mine did.
Have you said thank you to Jamie, or did you do that in the last video?
We did a coffee shout out actually on these.
I was there.
Yes,
Oh,
you were there.
I was there.
Well done.
But didn't we say thank you to him? It's fine.
Fuck him.
Fuck him. Okay,
Basically.
fine.
Right.
It's
that's
mad that
enough.
you said.
This video's too long. It's already too long and no one's watching anymore. Let's go and have a wee.
Jamie's
Not
mum.
at the same time, separately.
Jamie's mum.
I'm not weeing over her.
Let's suspend this quickly.
Not doing that again. She does like it.